Hello, welcome. So in this series, we're building this computer processor, and so far we've got a Fibonacci sequence, and in previous videos we built some nice fancy blinking lights. I plan to expand this in the future, but for now I'd like to do something else. So if you've been watching previous videos, you probably may notice something is different with the sound. I got a new microphone. Yay! I was having quite a few issues with reverberation and other things happening with my previous microphone, so I thought I'd invest in something a bit better. It may take a video or two before the settings are just right, so bear with me on that. I think I have the volume the same as the previous video, but it can be hard for me to tell. So let me know in the comments down below if you have anything to say about my settings, and hopefully I can adjust. So let's get into the topic for today. We have an assembler right here. This assembler is converting something that's somewhat human friendly into machine language that is stored in memory. And that machine language is then fetched and decoded in this processor. Now, machine language looks like this. It's just a bunch of binary ones and zeros. This is not super human friendly. So in general, most people don't work at this level in writing programs, which is why I have a bit of a circuit here to help me. But I am not finding this to be super human friendly either. I keep forgetting to turn on the programming mode. I edit that out, but that's kind of a waste of time for me. And also it takes quite a bit of concentration to figure out what the settings are for each instruction. And this is not going to scale very well because we're going to have to add way too many buttons. So all that said, I think it's about time that we move on to a proper assembler. And I do have a very good program in mind for that. The program is called customasm, and this is a customizable assembler. So you can find it on GitHub at this URL here, and I will put this URL down in the description down below on this video and following videos, so you can access it there. This program does have some Windows binary in the releases, so you can just download this if you have Windows. But for this video, I'm going to use the web version. So there's a web version linked up here, and it looks like this. And so I'm just going to copy and paste what I'm working on into here and compile it in here, and then copy and paste this into the other file. So a bit of a rundown of what you can find in here. There is some documentation on this processor here. It's not finished yet. I have tried to contribute a bit more documentation for some of the pages that are missing here. It is currently in review, but maybe by the time you're watching this video, this documentation will be a little bit more complete, but it does get you started at least. So a few releases ago, version 0.11, the syntax changed. And when it changed, this new user guide was created for it. So this user guide has the most up-to-date documentation currently. So if you're looking for how the program works, this is the first stop. But it's not complete. And so there is some older documentation in the doc folder here that has a bit more information, but you have to filter what you see in here by a upgrade document. So there's a migration guide from older versions to 0.11. So I think that's everything to mention here. Let's get into how this works. So the way that customasm works is you provide a set of rules that translate the assembly language that you want into the machine language. So that allows you to specify what your assembler or assembly language looks like, and then it will compile it down into machine language for you. Let's see if we can come up with a set of rules for the processor that we've built so far. So what I'm going to do is I'm going to jump into Visual Studio Code because I'm used to this program for typing. It's a little bit less clumsy than typing directly into a form on a web page. So generally, we start with how many bits is this processor? Because the number of bits affects what this program thinks is an address. And currently, the processor is not a byte processor, it's a word-oriented processor. So we have to set the bits to 16. In the future, this may change so that addresses are of bytes rather than 16-bit words. But for now, this is what we've built. And what we need to do is set up a rule def. And we need to set up some rules. So if we look at the current assembler that we have, this is basically what the machine language looks like, these bit patterns here. So we have 1 bit to specify whether it's a 2-register instruction or a 1-register instruction with a value. Then we have 3 bits to indicate the opcode. Then we have a destination register, which is 2 bits, and a source register, which is 2 bits, and a value, which is the remaining 8 bits. So let's translate that into a format. Let's see. We have an add instruction. It takes a destination register, which is a reg, and we'll get to defining the reg later, and it takes a value. So let's do the 1reg version of this first. And then we have the arrow, which indicates this is what it gets translated into. And the bits go from the most significant bit to the least significant bit, kind of like if you had the binary value. So if you had a binary value like this, then this is how the format is specified. The first bits here will be the leftmost ones if you were looking at the binary value. So going from left to right, then the most significant bits are going to be the value. And there's 8 bits. So the backtick and the number indicate how many bits from the variable it will put into the machine code itself. So we have a value. Next is the opcode. So the opcode in this case is 0, and we want 3 bits from that. And then we have RS, I believe, which in this case is 0 because we don't use RS, and that is 2 bits. And then we have RD, which is 2 bits. And then we have whether or not it is a 2-reg instruction, which in this case it is not. So we'll use 0 for that, and it's only a single bit. So this should be the format that we have, and we can test that out but we need to address this. This is the type of the argument, and you can specify a register in this case, but I want to give the registers names. That way we can do something like this. So in this case, we want to translate this into a number. So you can do that with a subrule def. So I am saying that there's a subrule called reg with some translations. Those are R0 is 0, R1 is 1, R2 is 2, and R3 is 3. So this should work. Let's copy paste this into the web mode of this assembler and see what happens. So there's a bunch of different options in here. One of them is to see the binary data, and this can be useful to verify that the fields are in the correct order. And we can see going from least significant to most significant, that looks correct. So this is R1, so this is the destination register field here, which is 1. And then we've got source register, which is not used in this case, so it's 0. And then we have the opcode, which is 0. And then we have 5 in the upper byte. So let's see. We also have hex, so we can verify that it looks correct in the hex mode as well. And we have logism, 16-bit. And this is what you would copy and paste into the processor itself, since digital understands the logism format. And I believe you want 16-bit. I haven't tried 8-bit. I'm not sure if the byte orders will be correct in that mode, but in 16-bit, then the byte order doesn't matter. So that's what I'll use. So let's expand this. The next thing that I want to do is add the toReg form of the add instruction. And note that you can have two rules with the same name, and it'll choose them based on the parameters. So in this case, I want to do rs is a reg as well. And then if I do this mode where I give it two registers, it will select this rule rather than this rule. So in this case, we don't have a value. This is 0, but we do have an rs, and we do have a toReg. So we specify that as a 1. So then we also have a move instruction. And the move instruction is opcode 6. And we have a jump instruction, which is opcode 7. And in this case, the destination register is not used. Also note that you can jump to a register. That's actually legal. I am not sure where that would be useful, but I guess we could add it just to be complete. I think it's actually rs that would be used. I believe the destination register will be ignored, but I'm not 100% sure on that. So this is kind of untested. I'm not sure if this will work, but we're not going to test it. Anyway, this should be enough for us to implement the Fibonacci sequence. Let's see if I can remember how to spell it. I believe that's correct. So the first thing that we want to do is, I believe what we were going to do is add 1 to R1. And this could be a move instruction now as well, but I'll leave it as add because I believe that's what we're using in the current processor. So the first instruction is it's into R2. Okay, I'm a little bit wrong on that. So we put 1 into R2. The next instruction is adding R1 and R2 and putting it into R2. And a note on conventions. Some processors, the destination or the register that you want to put the result into is on the left, and in some processors it's on the right. I think of this as this in my mind, or I guess in the case of an add, it would be this. So I'm thinking of the destination being on the left. So this is the convention that I prefer. You can use whatever convention you like, and there are many processors out there that reverse these. This just feels more intuitive to me, and it's easier for me to keep track of it in my head. So that's what I'll do. So we've got the add instruction, and then the next one is assigning R2 to R3. So we can do that with a move instruction. And then I believe we just do the same thing up here, but we swap the registers around. And we move R1 into R3. Let me just double check that. So yes, we swap the registers around, and then R1 goes into R3. And then the final instruction is to jump back to 1. Well, where is 1? Well, 1 is actually right here, and we can indent this, and we can say jump loop, like that. So this is called a label, and in fact, this is also a label. And that's one of the nice things about working at the assembly level is you can label things and let the assembler figure out what the address is. And the address of loop here, this dot just means that it's a sub-label of its parent label up here, which is why I indented it. You could also just remove that and put it at the root level if you wanted. And the indentation here is just to make it more human readable. It's ignored. So yes, so jump will jump to this label. It will automatically figure out that this is at address 1, and it'll wire that up for you. So let us save this and let's try it out. So let's see if this looks correct. And we've got this in the correct order here. So let's look at the values that we have in our EEPROM. So we've got these values here, and the first one is 120. Let's see if that looks sane. It does not. Why is that? 104. So the 1 looks correct. The 04 should be 20. I wonder. I think I have the opcode in the wrong spot. Yes, I do. Because if we're looking from right to left, if we look at this assembler here, from right to left, it's 2reg, then the opcode, then the registers, then the value. So I definitely have that swapped around. So let's just fix that. So the opcode doesn't go here. It goes here, I believe. So I'll just make that change on all of these. Another thing I'm going to do is just align the equals so that it's a little bit easier to see. And it might be helpful to line up the @ signs as well. There we go. That looks a little bit better. There we go. We've got our 20 here. Let's make sure that these other ones look sane. We've got 61 BD 91 7D. 61 BD 91 7D. So you'll notice that there's a 1 in front. Now, on these instructions, the value part isn't used. So when I was entering these in, I had a 1 still in the value from the first instruction, and I didn't set that to 0. So that's why these all have 1 on them. So what we're really looking at is the least significant byte. And we get 61 BD 91 7D, so that is correct. This one should be the same, 10E. Let's see if that's what we've got as well. 10E. Excellent. Good. Okay. So let's change this to Logisim 16-bit. And we now have the hex file. All right. So in here, I'm just going to go into here and find our hex file. And this is the file that gets loaded into the EEPROM memory. So I'm just going to replace this with our assembled value and save it. Don't worry about the formatting being slightly different. This works as well. So in here, I can go reload and it'll load the new program. And we can see that in here where the 1s have been removed from these. So it is loading the new value. And actually there's something else that we can do. In advanced, we can specify that this is program memory. And then when you do that, you can go into circuit specific settings. In the advanced, there's preload program memory at startup. So you can check that and you can specify a program file. In this case, it is in here, dig, test hex, open. And what this will do is every time you hit the play button here, it'll reload that file. So that allows you to change the file without having to go back into here and right-clicking on here and reloading it. So that's pretty handy. Let's test the program. Let's see if it's doing the same thing as before. That looks very familiar. So I believe everything is working correctly. So yeah, that's awesome. So I feel like now this assembler is no longer necessary. I feel like we can actually just delete it. So I'm going to. Let's move this out of the way and let's just delete it. We no longer need this since I feel like we have a better representation of this in our assembly program. And we don't need the crude assembler that we had. Now, PC we do want. Just fix that. And we have a bunch of unused pins here, so let's just remove those. We also have some unused pins on here, and I think probably the easiest is just to go in here and stub them out. So we no longer have a instruction in, and we no longer use this clock pin. So okay, I'm gonna just move this down here and move these down. There we go. I think it's roughly centered. Does that look centered? Maybe one over. There we go. Let's make sure we didn't break anything. So far, so good. Looks like this is success. Awesome. I think this is good. All right. So I think this is a good place to end this episode. We now have a proper assembler using customasm, which we're able to customize with the rules for our processor. And that'll come in handy in the future because the instruction set that it currently runs is very dissimilar from what it'll eventually run. And so it'll be nice to just change a few rules when we add new mechanics to how this processor works. So yeah, if you have any questions about anything, just leave a comment down below and me or somebody else will answer your questions. Thank you very much for watching and have yourself a great day. Bye.